So let's start. Uh, as far as my point of view, I think I explain you all the things which a beginner programmer in Matlab requires. For example, we started with Matlab minimum sessions, creation of variables, then how we can solve simple mathematical expressions, how we can solve simple mathematical expressions, and then we went into various control loops available. Then we went into how do we write a small script file, small codes like calculation of area, passing functions, function files, and then we went to how do we solve one ordinary differential equations, two ordinary differential equations, second order ordinary differential equation, or any higher order ordinary differential equations. And in last few lectures, we also saw how do we solve algebraic equations, which in general comes. All these coupled, and then matrices and various types of matrices now. How do we get the helps from MATLAB? How do we find out various commands in MATLAB? All these things we explained up till now. The basic purpose of building these blocks is that today or hereafter you should be able to solve or simulate a program in MATLAB. So when I say a program of a system. So if we have physical systems and we are able to model it, when I say model it means we are able to write the various phenomena of the system into mathematical expressions. And in a general, those mathematical expressions get resulted into partial differential equation, a set of partial differential equation, or a set of ordinary differential equation, or a set of algebraic equation, or a combinations of these. So, if we get a set of partial differential equation, first order differential equations, IVPs, we are able to solve it. If we get a set of algebraic equations, we are able to solve it. If we get a set of partial differential equations, we know from our mathematical studies that we can convert a partial differential equations into n number of differential equations, and that n number of differential equations we are able to solve. So, in a nutshell, if a system model resulted into any set of equations, we are in a position to simulate that in a matrix. So when we simulate that systems, we either try to simulate that system because we wanted to understand the system dynamics. When I say I wanted to understand the system dynamics means I wanted to see that if this forcing functions or this input has been changed in this forcing function fashions, what will be impact on my outputs? Because when we wanted to study any systems, we know what is output, we know what is inputs. Now we wanted to see that if I change my inputs, what will be the impact on outputs? If I get some concentrations, some contaminations in the input flow rates, what will be the impact on my outputs? Or if the system is first orders, how the response will be, in how many seconds time units the system is going to stable. So all these informations I wanted to find out. That is the reasons I wanted to do the modeling. And once I understood about the systems, I might in a position to understand or to explain what exactly happens in a system if some disturbance comes into the system through the inputs or through the disturbances. Correct. So that's a one way or one use of my modeling the system. Another use of my modeling the system is to design the control system. So when I design a systems, I design that steady states. I really don't know how the system will behave in a dynamics. So that dynamics I will understand it from the dynamic study. Once I understood dynamic study, it's the job of a system engineering or a control engineer to design the control of the system so that even if some disturbance entered into the system, the control system which you design and assign to the system should be in a position to navigate that disturbance. Correct? Or the another use of modeling or simulating is to carry out the optimization, because there are a number of input parameters. So where do you wanted to operate your system such that you can get the optimum outputs from your system with a minimum expenses. So that's another way of doing a mathematical model. So all this can be done in Matlab. Here, I am going to explain only one thing. That's how do we design the how not how to design the control. I'm going to explain how do we implement the control systems in Matlab. So with this, I am going to explain you a little bit about the control system. I am not going to go in a very deep into the control system, but what are the things which are necessary for this course? That is where I am going to explain. I'm going to restrict myself only to that portions. It is not my purpose to dwell into your process control and instrumentation course. In no way I am going to go there. I am just going to explain what are the things is necessary from the modeling point of view or from the simulation point of view in MATLAB. Okay, so what do you do? Whatever I explain up till now, you take a 2 minutes break and try to understand it, whatever I am just now told. So, is there any questions on what I tried to explain in just a few minutes back? So, let's start understanding the control systems. So, let's assume that you have one physical system. We will take a very simple example. So, we have a systems like a water tank. Correct? We have a tank. Very simple example I am taking. Okay, and it has its chloride. Let's say this chloride is Fi, you get again unit, correct? And it has one hole from which the outlet chloride, and let's take outlet chloride as Xg, correct? And water. Correct. So this is a system available. Now we wanted to control this. The objective is to control this system. Okay. So what would be my control objective here? Looking at the description of the systems. So can you people guess what is my controlled objective? What the things I'm going to control?
So the height of the tank,
Sorry?
uh, height of the tank,
Okay, height of the water content. Correct. So you mean to say this level. Agree? So my control objective is is water level of the tank. So, now, how do I control it? I mean, what I need to change, or in other way, I can put the question like, what are the things which going to influence on the height of that water content or water level?
Sir, input and output flow rate and diameter of the tank.
Okay, so let's say input flow rate, output flow rate, diameter of the tank. Anything else? Is there anything else which can influence the water level? Okay. So let me tell you, control engineers comes at the end. Okay. So whenever system is at place, whenever the design of the system is fixed, okay, and then control engineer's enters, and then he tries to design the controller. So if that is the scenario, then I cannot change diameter of the tank. Agree? That's the one reason. Another reason is, let's say let's say this height is 0 centimeter, for example, and this is meter, sorry, 0 meter, and this is 5 meter. I have the tank which is fixed now. It is in front of my eyes, and the first goal for me is to maintain the level at 5 meter. Okay, so what will happen? I can change the input flow rates so that height goes to 5 meter, or I can change the outlet flow rate so that the height goes to 5 meter. It goes to 5 meter. Okay. Now, I let's say the second goal during the operations came to 7 meter. Okay. So in that case, I cannot change the diameter of my tank. So what I'm trying to explain, or what I'm trying to tell is that diameter of tank is not something which can be changed dynamically, which can be changed with time. Correct? So diameter of the tank is not the viable options here for changing the water level. Okay. Now, so I can pick the two. That's the input flow rate and output flow rate. So which one of these is a good variable for controlling water level? How do you find out that? Any idea? So if I pose the questions to you is that which one of these I should take, input flow rate or output flow rate as the variable for manipulating water level of the tank?
Input flow rate.
Yeah. So someone says input flow rate. Is there any other answers? input flow rate is a correct answer, but how do you came to that one? Why do you think that the input flow rate is the answer? Do you think that the input flow rate might be the good variable for manipulating water level?
Sir, if we take the output stream into some other reactor also, like in industries, we take things in series something. So variable, if the output stream is kept as variable, then other processes would also require optimization according to it. But keeping the input will help only to optimize this one, and the other can be optimized at their requirements if we think in that way.
Okay, let me explain you which one we should go about this. Okay, so what we basically need to do. So here we had a valve, for example. Here also we have a valve. We need to find out, basically, see, when we controlled something, or when we wanted to manipulate some things, the only reasons are or we will select the variables such that the selected variable for manipulation should have maximum impact on my outputs. Correct. So here my output is water level of tank. Now if you are choosing a variable which does not have much impact on the output level of the water level. So let's say for example, if we have Fi, now Fi has a very minimal impact on outputs. So you can change the flow rates, but your height is not increasing much. Then there is no point in selecting Fi as your manipulation variable. Correct? Or in vice versa, if your FO does not have capability to change the height in both the directions, that increasing height or decreasing height, then choosing FO is not the good options for manipulation. So how do we find out this? The simplest way to find out this is by using the forcing functions. By using the forcing functions. So we have state forcing functions, we have impulse forcing functions, we have ramp forcing functions, we have pulse forcing functions, so on. Correct. So one of these forcing functions, and in this case, we in general take the step by the forcing functions. And what we do, we give a step change into this plan. Okay, so we give a state change into this plan. So we are changing the flow rate Fi and try to find out how the level here changes. So mathematically, or or picturally, if I wanted to say, let's say Fi, so you might be knowing that this is the state response. So here is my Fi initially, and this is where the time of step change. And if I given a step change of positive, then let's say I given like this. So this is 0 here. So here I say T1 and here I say T2. Okay. So in a similarly, what I am going to do, so I know the sampling time. So I get the measurements from here, height measurements. Right? So I will measure the heights at every sampling time. And if I plotted that here below this curve, so I take height as an h, and with this is my time t1, this is 0, and this is, let's say, t. Correct? So initially, this flow rate is constant, so my height will be constant. And after this, I'm changing the flow rates. So this height will also change according to its own dynamics. Okay, so this type of graph I will get. That is what is the study of dynamics. So what it tells me various things. Tells me various things like tells me what is the settling time of the system. Okay, it tells me what is the sampling time of the system. It tells me type of response. It tells me what is the steady state gain of the system. Correct? So these are the informations it provides. It also tells me sign of the gain. Correct? So let me explain you these terms. I don't know whether you know these terms or not. I'm going to explain each and every terms. So these are the informations it provides me, and this information is useful for me to decide which of the manipulated variables I should select if there are more than one manipulated variable for controlling a particular output. So, for example, settling time. So settling time means if this is my ultimate response, let's say h infinity, then this green color line should come within plus minus 5% and stay there. That time is called as settling time. So this is what is the ES settling times of the system. Okay, so this is what is the settling time of the system. If once I know that my system is going to settle in a 5 minutes, 5 seconds, 5 hours. So I understand from that if some changes occurs into the system, then it's going to get over in next 5 minutes, 5 seconds, 5 hours, whatever may be the time constant. That's information we give by settling time number. So once I got the settling time, I do understand that at what time I should sample my system. So at what time rate I should get outputs from the systems. Okay, so that I can reconstruct the signals very well. Okay, so the thumb rule is that sampling time. Okay, sampling time, and then one more here is the time cost. So once I got the settling time, time constant is basically settling time divided by 5. Thumb rule. Okay, this is thumb rule. I'm not going with a very strict mathematical formulas. Okay, so sampling time is equal to settling time by 5. Once I got the sampling time, once I got the sampling time, sorry, time constants. So this is time constants. This time constants. So the informations we will get by giving the step change is its settling time. Second one is time constant of the system. Third one is sampling time. Fourth one is dynamics of the systems. System basically order of the systems. Any other nonlinear things present in the systems. Correct. And then we get state gain, then we get sine of the steady state gain. Okay, so we understood settling time is when the response comes within plus minus 5% of ultimate value. Correct. So when we give the step change, ultimate value is that the system doesn't change after that step change. The height of the system doesn't change. So and stays there. That is the time I will say settling times. And time constants, thumb rule, I know the thumb rule as for time constants. So it's a settling time divided by 5, and sampling time is time constant divided by 50 in a general, in practice. Okay, so I give this information once I given the step change. So right now I'm talking about a physical system. Let's say physical system is in front of you, and now you have changed the valve of inlet flow rate. Correct? You change in a fashion of step change. How do we realize the forcing functions into the realization? That's a different topic. But let's assume that you change your valve from position A1 to position A2, and then you waited for the system's height to get settled. Once you settled, you find out the time. So that's your settling time. Then you find out time, and then you find out time, sampling time. So you understood. At this sampling time, I should take the output so that I can reconstruct the signals. Okay. Now, from this response, you also observed that the response looks like a first order system, because this response is the first order system. This does not have any other characteristics of the response, like does not have this way, it does not went this way, it does not went this way, correct, and it does not show this response. So these are all of the responses of the system. So our system at this point of time, which we are considering example, does not show any one of this. So we know that it's a first order linear system, almost linear systems. We understood from the step responses. Now, steady state gain. Okay, so what is gain? Let's take the gain. Gain is change in output. Change in output divided by change in input. That's value basically tells me if I change the Fi from a value of A1 to value of A2, my output height is changing from H1 to H2. So for example, going back to again the figure here. Here. So shall I say this is my value as H1. So before changing the value of the systems or flow rates, my value, sorry, my flow rate was Fi1. Okay, now once I change in a state fashion, it's supposed to Fi2. Correct? In a similar way, if I say the initial height was H1, and now after getting to the state change, it goes here as H2. So from this, I can find out change in output, which is H2 minus H1 divided by change in input, which is Fi1 2 minus Fi1. So I got my steady state gain. This value is going to tell me how much impact I have by changing my inputs on the output. Okay? And the sign of this will tell me whether it's a positive or negative. So when I say if it's a positive, it means that if I am giving a positive state change in Fi, I will get increase in powers. If this value is negative, then if I given a positive change in Fi, it means that my system is going to decrease the output. So basically, this information I will get once I have given the step change into the system. Correct? Now, with this information, I can implement the step changes on all other variables, which is the potential manipulated variables of the system. And By comparing all this with having the knowledge of which variable is good for maneuverability, because let's assume that if you have a concentrations, you come up with a concentration as the manipulated variable, and now you cannot change the concentrations of inputs so often. It's very easy to change the flow rates, but changing concentration so often is not possible. Then even if rest of all the parameters in terms of concentration is favorable, we may not go with the concentration as the manipulated variable until unless we don't have any choice. But if there is a flow rate which basically showing some of these parameters which I explained might not favor it, but still we will go to the flow rate. So considering all this, we will be in a position to select proper manipulated variable. So after selecting the manipulated variable and outputs also, we know the output of the system. We selected the manipulated variables. Then come to the selection of controllers or design of the controllers. Before that, I would like to know if anyone has any doubts on what I explained. Please ask if you have any doubts. Now we understood how to we select the manipulated variables, we know the control variables, and we have physical system in front of us. Now, if we really don't know the physical system, or we cannot construct the physical system, or we cannot give state change to a physical system. For example, if industry is going on, it's working and is in progress, and if a control engineer comes and says that I wanted to change this flow rate, the operator there at the plant will not allow you to change, because by your change you might get your objective, but there's a maximum chances that you are going to disturb the whole industry or whole process. So many of the engineers will not allow you to change. So in that sense, what we do, what the options in front of us, we understand the dynamics or the physics of the system, and then we try to build a model of the system. And once we try to build the models, we get the data from those guys and try to validate our model. And we say that, see, here is the experimental data and here is my model data, and these two are matching. It means that my model is representing my system. My model is representing my system. So what we have is the mathematical model. What a control engineer deals with is the mathematical model. So we have mathematical models, and as I explained earlier, it's might a set of ODEs, might a set of PDEs, it might a set of algebraic equations, or the combinations of these all. Correct. So we know how to solve this. So using this models, we should be in a position to give the state change and get the dynamics of this. Okay. So once we get the dynamics of systems, we are in a position to design the control. So let me portray a diagram for the control system so that you can understand. So in a simple example, I'm again taking a water level system. Okay, so I have here a set point. which basically what should be my content level. Correct? Content level. Okay. Then here is a control system box. Okay. And here is your physical system. I am first talking about physical system. Here is your system. Okay. From physical systems, you measure content level. Okay. You need to some measuring equipment which measure your content level. Okay. And then that measuring levels you will supply here. Get subtracted from this set points and this goes here. Okay, so we call this here. Set points desired value minus your current value is a set point which gives you the manipulator variable which is identified. That manipulator variable goes into yeah. Okay, so this is the block diagram of the control system. If there is a physical systems, let me draw with the physical system so that the understanding. So now we decided that we will go with this as the manipulated variable. Okay. And here is my sensor which basically measures my height. Okay. Now what will happen? So looking at this block diagram, I have a physical system. I measure this content level here. Okay, I measure this and then I am going to supply it to a component. So here is the controller, for example. Okay, so here I am supplying this value to the controller, and here is my set point. I am saying my controller that okay, maintain this at 10 meter or 15 meter. That I know because it will be coming from the operating engineers who operates the plant. Okay, and then this goes and change your these plans. This is the actual diagram. This is mathematical, this is the block diagram of the systems, and this actually will happen. There are some other components that not of need here. So this is the control system. So what I am going to do in this course, I am going to model these systems. Okay, I am going to model these systems. Once I model these systems, I am going to give a state change to the systems, understand the dynamics. Once I understand the dynamics, I know that I can go with classical controls at this point of time and then implement the code of classical controller and try to show that I am able to maneuver my systems from 5 meter to 10 meter to 15 meter. This is for this water tank system or any other objectives. Okay. So I'm going to explain to you now the classical controls, piece of classical control. So basically, we are dealing with only linear systems, and we are going to design only not designs. We are going to implement only linear controllers. Linear controllers are called as the classical controllers. There are basically three different types of classical controllers. Some people say it's four, but I would restrict myself to three. The first is P control. The second one is PI, and the third one is PIP. So this is proportional control. Proportional. This is proportional plus integral control. This is proportional plus integral plus derivative. This each one has its plus and minus. Earlier, when computers were not so powerful, people have hydraulics controllers or pneumatic controllers. So those were come in a block. If you want a P controllers, those will come in a block. Nowadays, everyone can be written in a software, and a software gets situated in a computers. Correct. So even if we say that these are the controllers, it's basically mathematical algorithm which basically calculates my manipulated variables. So here, if you look here, if you look this diagram, here if you look at this diagram, what it calculates m. Agree? Basically, at the end of the day, calculates m. This is what it's used. This is what is inserted into the system. M, which is the manipulated variable, or in this example, it's basically calculates percentage opening or closing of the valve. That's what is the manipulated variable here in a nutshell. Even if we are saying that the flow rate is the manipulated variable, that flow rate changes with the percentage opening of the valve. So the controller in a nutshell calculates M. Correct? So there are certain mathematical expressions for this, which I am going to explain you. So, for example, P is the controller. So, for example, proportional controller. So, proportional controller has the example or the mathematical expression as if I say m of E is equal to Kc into epsilon, Kc into epsilon of T plus m. Yes. So let me explain this equations. So now, once we started controller, before that, this valve might have some opening. Correct? It either might be a close, it might be 10% open, it might be 15% open, it might be 13% open. So basically, what we are defining a steady state. We are defining the steady state at which I wanted to start my controlling operations, or from which I wanted to start my controlling operation. As this steady state has been defined, it has defined what is the percentage opening. There's a 10% opening, there's 20%, 30%. So this value is already there. Okay. Now I know this value. Fine. I know this value. This is the separate topic of designing of the control. In this course, I am not going to touch this designing of controllers. So we can get this value directly. Okay. So in these equations, we got Kc, we know Ms, and epsilon t is the error at that time frame between the set points and the measurement. Correct? So set points, I know because I am the person who are going to control the system. So I know that I wanted to control it at 7 meters or control it at 10 meters, control it 5 meters. So I know the set points. And measurement, where I am measuring the content level after every sampling is done. If there is a physical system, I will put the sensor. If there is not a physical system, I have the model, then this model should have these informations. Correct? This model should provide me height. Correct? So that model has that. dH by dt is equal to fi minus x0. If that is the model I'm writing for this simple example, dH by dt is equal to fi minus x0. Correct? Then if I solve these differential equations, I get H. So that is what I'm getting from the model. So, so I got the measurements, I know the set points so that I can find out the epsilon. So once I found out the epsilon t, I can get the m of t. So here in this case, in this example, it's a percentage opening value. So initially, if the steady state output is 5 meter and my set point is 7 meter, correct? And input steady state is 2 meter cube per second, for example. Correct. So as soon as I given the set point, which is the 7 meters, so error, which is epsilon t is 2 meter, correct? And you set ms 2 meter, again 2 meter is per seconds is a ms plus AC I would say as zero point 0.5. So I got so this is epsilon t, and I have ms at this point of time as 2 meter cube per seconds, and Kc is constant for this controller as zero point 0.5. Then I get m of t as Kc is zero point 0.5 multiplied by epsilon is 2 plus ms is 2, which is 3. So earlier my ms inputs was 2 meter cube per seconds. Now it's saying that give it 3 meter cube per second. Now, with this 3 meter cube per seconds flow rates will go into the systems that will change my height, and let's say that height becomes 5.5 meter. Again, the second time, this is for the first 0 instance, this is for 1 instance, this is for second instance. Again, this might going to change to 3.5 meter per second, this becomes 6 meters. Third, this goes to 4 meter cube per second, it becomes 7 meters. Correct. So a time will come when my output value becomes equal to my set point value, and I say I maintain it at. So this is the proportional controller. Now in PI controllers, you can add the integral terms. So in proportional controllers, we saw this, and in PI controllers, we can add these terms as for PI is m of t is equal to I have Kc epsilon of t plus Ki integrations from 0 to t e epsilon of t plus your ms. So here this time is as it is for the proportional control. Here I added the integration. Integration is continuous is addition into the uh, discrete terms. So I might be able to calculate dm of t with the given information. In a similar way, I have PID controllers where here one more term that's KD d epsilon by dt adds. Correct. So these are the classical controllers. Now the questions of calculating Kc, Ki, Kd is part of the designing of the controller. There are plethora of methods available which you might want to get into your PCI class. Here now with this, our job is to make the code for this. So we have a code for systems, we will have a code for controllers, and then we can combine these two such that the flow of informations takes place. The flow of informations will basically going to take place from your block diagram. The way here you have block diagram. So from the models, I will get the outputs. That outputs I will supply to the control code, and control code takes that output. It has its set point. It calculates error. It calculates my manipulator variables. That's the percentage opening up for, and that goes into again the physical system. With the new value of manipulator variables, I am going to solve my physical systems and gets my content level again. And I will repeat this for so many times such that my set point equal to my content levels or my outputs. So this is the logic I should developing into the Matlab. Okay. So if there is any questions, please let me know. I'm going to stop here for just for 1 minute, and then I'm going to tell you one more thing. Okay. As you don't have any question, it seems that you understand it completely. However, unfortunately, that is what not demonstrated in examinations. And I also know how you people given the examinations. I really don't want to go into that one, but I am just performing my job. Maybe you say physically or emotionally, it doesn't matter. So now what do you do? The assignments for next week is that every one of you came up with a physical systems which has, let's say, two ordinary differential equations or three ordinary differential equations. Solve that systems in your MATLABs. Keep ready that programs. Okay, keep ready that program. Every one of you has to find out systems like a water tank, heating tank, mixing tank, or any other examples from the literatures, which has basically two to three differential equations. So you read the description about the systems, find out which is the input manipulated variable, which is the output variables, and code that into in your MATLABs. Correct. Make ready in the next class, and then I'm going to tell you what we will going to do with the data systems in next 3-4 class. We will work exclusively on your own systems. So the system should be different. So I'm expecting at least 26 systems. Okay, next Monday. Thank you.